Okay, so it has been a while since our last meeting. Let's recall some of the important notations. You have concept theorems, of them. We start with a right triangle. Okay. We call this side the hypotenuse side. These two sides, there are the two legs. They may have different names. Just for our course, we use these two terms. Okay, and there's a very important theorem for any right triangle. If we find the midpoint, of the hypotenuse side, then we connect the 2 points. The side is half of AB. So this is called the hypotenuse side mid theorem. You know how we proved this? George, let's remove the feature. Uh, okay. And we also introduce this sufficient conditions and necessary conditions. Sufficient conditions. A very simple example is if it rains, the road is wet. Okay. We can see if it rains, the road is wet. This is sufficient. The raining is sufficient for wet road, but wet road is not sufficient for raining. Maybe because there's snow, there's ice, there's someone just poured water. P, P, Q, P, and Q. On the other hand, we can see Q is a necessary condition. Okay. For it to be raining, the road must be wet. This is a necessary condition. Sometimes we have a condition that is sufficient and necessary. The first one, according to our definition, P is a sufficient condition of Q. The second one, according to our definition, Q implies P, the P is a necessary condition of Q. Therefore, so P is this one, P is sufficient. And this one implies P is a necessary condition. In this case, we see that the P is sufficient and necessary, or necessary and sufficient. So we have the short notation for these two relations. Necessary and sufficient. So one implies another. Take okay, yes, okay. George, go ahead. Okay. Now we can examine the various theorems we learned before using these new necessary and sufficient conditions. For example, the midpoint theorem. Initially, the statement is I think I used E before. Then we proved that F is also the midpoint. Let me write over there. Move this over here. Move this. Midpoint of AC. Okay, that's how we proved the theorem. We start with the midpoint, draw a parallel line, then we check this is also the midpoint. So now we can see this is a sufficient condition for F with midpoint, a sufficient condition. But we can go the other way. We check if this is the midpoint, two midpoint, then this must be parallel to BC. We can go the other way. Now we get to the conclusion that this is a necessary and sufficient condition.
Question.
Yes.
Couldn't we say E is the midpoint of AB?
So this is the setting. So uh,
Oh,
yes, Aaron. Uh-huh.
nothing.
Okay. So later we will generalize this. So why I put it over there, later we will drop this requirement. We have a very big theorem over there. Okay. So next one we have is the intercept theorem. You see the difference and the connection between the two theorems. Again, we start with a triangle. This time we pick an arbitrary point. It doesn't have to be the midpoint, Aaron. That's maybe what you were asking. This time we don't have to be midpoint. Can pick anywhere. I can pick a point over there. Then I draw a line of A, B, C. The intercept theorem tells us if EF is parallel to BC, then the two ratios are the same. Okay, that's how we stated the intercept theorem. But we also verified if the two ratios are the same, this line must be parallel. So we go the other way. The intercept theorem now becomes a theorem about necessary and sufficient condition. The two lines being parallel is necessary and sufficient for the two ratios to be the same. If we compare these two theorems, there are similar conclusions, but this is more general. This is a special case. And very surprisingly is the hypotenuse. Let's draw a right triangle. Not necessary, okay. A, B, C, D. Previously, the way we stated the theorem is if this is the right triangle, then CD is half of AB. So the initial statement, let D be the midpoint. Okay. This is how we initially stated the theorem. Then we can verify it also goes the other way. Previously, this is a sufficient condition for this to be half of AB. Now this is also a necessary condition for CD to be half of AB. That means whenever we have a triangle with this median to be half of AB, then this angle must be a right angle. Okay, so this is about the necessary and sufficient conditions. We will encounter more examples in the future. Any question about this at the moment? Aaron?
Question.
Uh-huh.
I'm gonna be learning about harder theorems after this.
Okay, you want harder theorems. Okay.
I'm asking if.
Okay, we will learn quite a few very difficult ones today. And Amy and Jessica? All right, okay. No, I assume no questions. So the difficult theorems about trigonometric functions. Sometimes I will use trig for short, and you will see this very often. Trig functions, they're short for trigonometric functions. Two basic one, consider a right triangle with angle theta over there, then you can define two functions. The leg facing the angle over the hypotenuse side, BC over AB. You can define another one, cosine theta equals BC. When you see this definition, it looks very natural. But here, implicit, maybe subtle issue is if we choose a different right triangle with angle theta, we consider the ratios, let's see, E and F. Are they the same? So a subtle issue in this definition. E, F. If we consider this right triangle, I have a second formula for sine, second formula for cosine. Okay, now my question is, do they define the same function? Are these two sine theta the same? Because theta is the same angle. Why are these two ratios the same? Okay, so why the two ratios? Similarly, y, the second two ratios. If the two ratios were different, then the definition will be problematic. What is sine theta? If I change the sign, do I get a different sine theta? We shouldn't. Amy, what's your guess? Why are the two ratios the same?
Um, it's like sort of like the intercepts theorem, I think.
Uh-huh. Okay,
But
why it's
it's like,
applicable? Uh-huh.
um, so if you like mirror the triangle,
Mm-hmm.
like you flip it and then you make it into a bigger triangle, and then you like uh turn it this way, it's like the same thing as like,
Okay.
yeah.
Uh-huh. Okay. So the key point, the key step is to observe that these two lines are parallel. The two lines are parallel, the two triangles are similar. They are similar, the corresponding ratios are the same. Okay, so the key step is to observe that EL parallel to BC. EF. This implies the two identities. This is the intercept theorem. Okay, there are different ways to argue this. This is the one way we have done before. So the intercept. Okay, so this is the key step. Jessica, from the conditions over there, how do you conclude these two lines are parallel? What theorem, what property do you use?
I forgot.
What's that? I'm sorry.
I don't know.
Okay. Think about it. It's okay. Uh, and Aaron, why are they parallel? Amy,
Because they have like a 90 degrees angle.
Okay. Okay. So these two angles, they are the corresponding angles for these two lines. The two angles are the same. These two lines are parallel. Jessica, does that make sense? Okay. Because the corresponding angles are the same measure, the two lines are parallel. Then the two triangles are similar, the ratios are the same. These two functions are well defined. Okay, one by one. Mm, So a very important theorem, the Pythagorean theorem. Now we can apply it to the right triangle. Let's consider a special case. Okay, now we consider a right triangle with the hypotenuse side of length 1. Aaron, what's this length?
Cosine,
Cosine or sine? How do
uh,
we decide?
sine, right?
Okay, so sine is the ratio of the side facing the angle.
Yeah.
Okay, so this time, this is the side facing the angle. The length will be sine theta.
Yep.
George, what about this one?
What?
In this right triangle, the hypotenuse side is 1. What's the length of this one?
Cosine theta?
So this will be cosine.
1
And
minus since to the second power, the square root of 1 minus sin to the second power.
okay, we will use that formula, but not at this time, this moment. Cosine theta to the Pythagorean theorem that George was using. So the Pythagorean theorem says that for a right triangle, the summation of the squares of the two legs equal to the square of the hypotenuse side. Do we get the square? Okay, so uh, this we use a short notation. Sine square is defined as the main reason that we introduce this is we don't want to write the parentheses every time. Whenever you see sine square, you should interpret it as sine theta then square. Same way. The Pythagorean theorem. A very important property of these two trigonometric functions. And then we define another two trigonometric functions, tangent and cotangent. Tangent state is defined as a ratio. You see the angle, the side facing the angle over the side adjacent to it. In the same way, cotangent is the reciprocal. So two new functions. So this is tangent with TAN for short, tangent, and the cotangent with COT for short. Similarly, the sine and the cosine.
I do see a slight variation.
What do you mean?
I see some difference between sine and tangent.
Uh-huh. Okay. So what's the difference? Sine and tangent.
Can you pull back up to confirm? I want to confirm. Yeah, sine's BC over AB, but tangent over it's BC over AC.
Very nice. That's a very good observation. So sine is the ratio of
Between
the side facing the angle with over the between the side. However, tangent is this two ratio. And the connection of the two, if we divide both numerator and denominator by AB, BC over AB, AC over AB. Okay. We divide the numerator and denominator by the same factor, the ratio should be the same. Now we realize this is sine, this is the cosine, so tangent. Tangent is the quotient of sine over cosine. Similarly, cotangent divided by the same factor. So very often we will use this as a definition of tangent. So this is a geometric meaning of tangent. It's the ratio, and this is the definition. And from the definition, we can also see cotangent is the reciprocal of tangent. Okay. Now, two special cases. What happens if theta becomes smaller and smaller? Theta goes to 0. Okay, think about this. What
Question.
if, yes,
What's that O thing next to that other O?
uh, where?
The one on the
Here?
yeah.
Oh, so when theta approach 0,
Uh-huh.
what happens to these four functions?
Oh.
So when this becomes smaller and smaller, let me rewrite my 0. Let me draw a picture with very small, not small enough, with very small. Okay, so we can see when the angle becomes small and small, when it approach 0, the side facing it is also becoming smaller and smaller, approach 0. In particular, sine theta approaches 0. Cosine theta, so these two sides will become closer and closer to the same. The ratio will become closer and closer to 1. tangent is the ratio of the two. When the numerator becomes smaller and smaller, denominator becomes 1, this goes to 0. Very natural. Now the last one. What happens to the cotangent when the angle becomes smaller and smaller? Amy, what do you see?
That
So this time cotangent, this goes to 1, this goes to 0.
Would that be like undefined?
And defined. All
would be
right. So
like
this will go to, yes, George. Okay. And
the same
defined.
like reciprocal and stuff, you know.
Uh-huh. So this is a big difference between this, give a big difference between these two functions and these two functions. This one both can be defined when theta.
Mhm.
However, for tangent and cotangent, okay, so the domains. Okay. For tangent, see, it can be 0, but for cotangent, it cannot be 0. Now, if theta approaches 90, we have the opposite phenomena. So this cannot be 90. Pay attention to the difference of the domains. Okay. So using right triangles, we defined the trigonometric functions for angles between 0 and 90 degrees. If we want to go over 90 degrees, we cannot use right triangles. We go over this. Okay, Aaron. Okay. Okay. So let's draw a right triangle and a more general. So this time, to define sine and cosine, we extend this and draw a perpendicular line. So sine defined as AD over AB. Still the two ratios, but the cosine will be negative. Okay. Very big difference. Sine theta is still positive, but
Question?
yes,
Why is it negative?
why is it negative? So later we will introduce the circles
Okay.
in chapter 5.
Also
So
some
later,
uh,
and over there we will extend this sine and cosine to any number. Could be 90, 180, 360, could be negative. Then we will define sine and cosine for any number. So over there, it will be more transparent, more easier to understand why this is a negative. So for the moment, let's just remember for angles between 90 degrees and 180 degrees, sine is positive, cosine is negative. Okay, so next chapter, we'll learn more about this. We sine x, cosine x the real number. Okay, so let's have 5 minutes break. I'll be back at 8:18.
All right.
Okay. Okay. So these functions, we define these functions, we used right triangles, but afterward, they can be applied in a study of any triangles because they have been defined. Whenever we have a 45 degrees, we know sine and cosine, we know this. So applications to more general triangles. Okay, let's draw a general triangle, not necessarily a right triangle. Okay, so we have few angles. Maybe I can change this, make it less symmetric. A, B, C. Now this is clearly not a right triangle. We have three angles over there. Angle alpha, beta, gamma. And the three sides, I will use this lower letter A, B, C for short. Okay. Aaron, is that some effect? Okay, okay. So,
Use the Greek symbols.
oh, okay. So this will be alpha you can use ABC, because we want to use the lowercase ABC for the size. Otherwise, I will use ABC.
All right.
Okay, because I reserved these letters for the size, so I introduced the Greek letters, beta and the gamma. For these three angles, we
Teacher?
can compute the sine and the cosine.
Teacher?
Yes.
Is gamma just like an open topped 8?
Kind of. See how we write gamma?
It's so weird.
Yes, yes, it's a little bit different. So it's more closer to R. R, but go up. Okay, let's see some applications of this. Now let me draw a perpendicular line. Okay, let's see, we have a lot of information over there. We have angle beta, angle gamma, have the size, the sides. Could you give me an expression for this length? We call it the height. What's the height of this right triangle, of this triangle? Using trigonometric functions, using the size, angles, whatever we have on the graph. Let's check.
So
Let's consider,
It's
yes,
perpendicular to BC.
try that again, I'm sorry.
It's perpendicular to BC.
Yes,
can we just use what we learned in like these, I don't know how to call them, things.
BC. Okay, so this is our condition. We will consider the right triangle, A, B, D. Okay, so George, in this right triangle, how do you express sine beta?
What? Like, what do you mean by express?
So using the ratios of the sides,
That like what we did before?
was sine beta,
A over AB, I suppose.
AD over AB.
Yeah, same thing.
Now if we multiply both sides by AB, we get the formula for AD. This implies okay, now let's apply the same thing to a different triangle, triangle ACD. Again, this is a right triangle. Sine gamma. Amy, do you find a formula for sine gamma in this right triangle?
It's kind of
I
like
don't
the
know.
old thing reversed. Not like the old, like the thing we did before, but you just like do it and like, yeah, I don't even understand myself.
Okay, so we have a right angle over there. So this is a right triangle. So sine gamma will be the ratio of the side facing gamma over the hypotenuse side. It will be AD over AC. Okay, so we multiply both sides by AC. Okay, question about this step. The first one, we use the left half to get the formula for AD. We use the right half to get the second formula for AD. All right, the two formulas for the same segment, it means they must be the same. So we have so more would be more interesting if we put this into the ratio sine beta. This is a very interesting formula. What does it mean? It means in this triangle, the ratio of sine beta with AC is the same as the ratio of sine gamma over AB. No matter what triangle we have, the two ratios must be the same. The sine of the angle over the length of the side, sine of the angle, length of the side. If we rotate this, sine of the angle, length of the side. So this is the law of sines for any triangle. We use alpha, beta, gamma, A, B, C. The ratio, the sine of the angle over the length of the side will be sine alpha over A. Two expressions, A, B, C.
Hey, teacher, is this like
E-
C squared equals A squared plus B squared and like cosine C or something?
Um, that will be the next one.
Oh.
This is the law of sines. What you mentioned is the law of cosines.
So this is like sine C?
Yes,
Oh,
sine
man.
over A, maybe BC, sine beta over AC, sine gamma over AB. An equivalent way, if we use the sines, sine alpha over A, sine beta over B, sine gamma over C. A very useful theorem for any triangle. It doesn't have to be a right triangle. We still have a lot of information about the sine of the angle and the length of the side facing it. So this is law of sine. Next, we have law of cosine. And how do we find this law of cosine? It will take a while to get the formula. We will start with the special case.
We have a question.
Yes.
So you're saying what's going on? So it's like sine beta is basically adjacent to AC, right?
Facing AC.
Yeah, it's like they're on the same side, something like that.
I'm not sure what
Like
if that's
con
huh?
like congruent.
Okay, yeah, you can see that. This is the opposite opposite side.
Uh-huh.
Uh-huh. Angle opposite side.
Yeah.
Angle opposite side. Sine of the angle the opposite side. Sine of the angle the opposite side. The ratios are the
Yep.
same.
Yep.
Okay. We can start with a special case. If we have a right triangle, too special, let's make it more general. Again, I will use the lowercase letters for the edges. This will be C, this will be B, and A. It's a very the Pythagorean theorem, so A square plus B square equals C square. Okay, we know this very well. This is true for right triangles. Now, if we have a triangle has no right angle, what do we have? A, B, C. Again, let's use lower letter for the edge. A square. So this time, this is not a right triangle. The summation will be different. But how different is this? We know it's different, but what is the difference? And this is another way to check if a triangle is right triangle or not. If the difference is zero, it's necessary and sufficient for this to be a right triangle. If it's not a right triangle, right angle, the difference will be not zero. But what is the difference? What's this non-zero term?
Like greater.
Okay, sometimes it's greater than zero, sometimes less than zero. They make changes. Okay, to find the formula for the difference. So maybe we can view this as the deficiency for the triangle to be a right triangle. How far is it from the right triangle? If there's no deficiency, then it must be a right triangle. If there is deficiency, what it is? Okay, to find the deficiency, I'm going to draw a perpendicular line. You see, this is a very useful method, draw perpendicular line. We will focus on the angle C. Okay, now the same question. AD. We want to check the difference to C squared. Let's see what's C squared. Let's start with C squared. Okay, so now we can see this is a right triangle. We can apply a Pythagorean theorem. C squared will be AD squared plus BD squared. That's very easy. I've done this many times. Okay, so now we will need an expression, a formula for AD. How do we express AD using this angle C? I've done this before. George? Okay, maybe not. I thought you were reading the questions. So
Yeah.
AD equals something, something, angle C. What is this? Should it be sine or cosine? Aaron.
I think it should be, what's it? Right, it's It's a cosine.
Okay, so sine is the side opposite to the angle. Cosine is the side adjacent to the angle.
Right.
So here, this is the opposite side. We should use sine.
Right, sine. Sorry,
Okay,
I meant sine.
okay. Okay, now what's this missing part? And Amy,
Mm,
in the right triangle, what is sine C? Sine C will be the ratio. Sine C equals AD over
DC.
AD over, if it's a DC, that will be tangent.
Oh,
It's
AC.
AC. Okay, the hypotenuse will be AC. So now we see here is AC. No, AC. What about CD? Again, there will be something, angle C. Jessica, the right triangle CD with sine or cosine over there.
Mm-hmm.
So this time it's the adjacent side we use cosine. And the cosine angle C will be CD over AC. Okay, so here we also have BD. Now, so BD will be the difference. So BC subtract CD. This equals to, okay, now we will put everything AD, BD, CD into the formula. I will continue from there. So C squared, because I will copy the formula before. AD is AC sine angle C squared. BD is BC subtract CD squared. Okay, so I used the formulas just derived for AD and BD. So I will continue. Let's see, AC. In this triangle AC is the edge B. The first term will be B squared sine squared. Okay, second term, BC. BC is side A. So I can replace BC by A. CD. CD is this. AC cosine. Okay, AC. AC is B. A little bit algebra, nothing difficult. A minus B cosine angle C. Okay, let me pause for a few seconds to give you time to process this and ask questions.
Can you follow up? Okay.
Uh-huh. So I draw a perpendicular line. Then in this right triangle, I apply the Pythagorean theorem. So AB square, the summation of these two squares. AB is our side C. Now AD, we find a formula for AD. AD is AC sine angle C. We find a formula for CD, AC cosine C. Then BD is the difference. Okay. Then we plug these two formulas into our expression. So AD replaced by this, BD replaced by the difference. So now simplify a little bit. AC is B, BC is A, AC, B. Okay, now a little bit of algebra. What's the square? How do you distribute the square?
You square the binomial.
Okay, so how do we do that?
You copy that and then distribute the A to the A, the A to the B, cos square root T, and the same thing.
Okay, so let's first maybe check a formula. X minus Y square. What's the formula, Aaron?
Right, it's you distribute the X to the X, the X to negative Y to negative Y, and then vice versa.
Okay, so this is the formula applied to this one. We have A square. Subtract twice of the product. And the last term is the square. All right, a long formula, but there's some cancellation can be done. So B square is a common factor. If we pull out the B square, we're left with sine square plus cosine square of the same angle. Very important simplification. Okay, let me check with you. How do we simplify this? Who knows the answer? Amy, I think you know. Do you?
No.
No? Okay. So the summation of two squares. So this is the special case of the Pythagorean theorem. I will go to the maybe as the first page or second page. Oh, over there. The Pythagorean theorem. The summation of the square, cosine and sine of the same angle will always be 1. The Pythagorean theorem. Now we apply the Pythagorean theorem. We recognize this is 1. Okay, so what we have obtained is C squared I will copy a square first. B square times 1, just b square, and the last term. Okay. So this is called law of cosine. In particular, it gives us the difference. In particular, the question we asked before, what's the deficiency? The difference is 0 when the angle is right angle. If it's not right angle, what's the deficiency? The deficiency is given by cosine. In particular, we have checked if this is 90 degrees, cosine 90 degrees is 0, so this term goes away, we get the Pythagorean theorem. If angle C is 90 degrees, cosine 90 degrees, we checked, this is 0, so C squared. Okay. We recovered the Pythagorean theorem.
Question?
Yes.
Hold up. Where'd you get the C squared again?
You mean over here?
Oh, wait, no, never mind, never mind.
Okay, yeah. So
No, I want you to pull it down because something doesn't. Uh, where that sin squared angle C plus O.
yes, Aaron,
I
finish
was
your
gonna,
question.
I was gonna say where that sin squared angle C plus cos squared cosine squared angle C go? Because I don't see it in the.
No, nothing over there. Is that your question?
Yeah.
So well, here we have b square, sine square, cosine square. But now we only have b square. What happened to this term?
Mm-hmm.
Amy, what's your answer to this question? Because we applied the Pythagorean theorem for right triangles, the sine square plus cosine square equals 1. Then b square times 1. Aaron, what's the b squared times 1?
That's still B squared. Oh, I see.
2b squared, right, yes. So this is a very important step. This is simplify our formula. Okay, okay, so this is a special case.
And I thought you said we never recovered the Pythagorean theorem. I thought you said that.
We recovered. Okay, maybe I misspoke. Okay, so another way to express this law of cosine. Let me recreate the triangle. We don't have to go back and forth. A, B, C. Angle C, lowercase c, lowercase b, lowercase a squared. It's the same as we had before. I just reorganize the terms. In particular, if we divide both sides by 2ab, we get law of cosine. It tells us if we know the sine of the triangles, then we can find the cosine of each angle. Cosine C is a squared b squared minus c squared over 2ab. Okay, we have a few minutes. Let me ask you, what about the cosine A? Do you have a formula for this? Cosine A, cosine B. Okay, so the rules is cosine of the angle, summation of the squares of two adjacent sides, subtract the square of the opposite side, divide by twice of the product of the two adjacent sides. Okay, if we have cosine A, what are the two adjacent sides? Amy.
Would it be like b squared plus c squared minus a squared over 2bc?
Very nice. So the summation of the two square of two sides adjacent to it, subtract the square of the side opposite to it. George, let's try cosine angle B.
The same thing, but just replace
So this cosine B, what are the two adjacent sides?
BA and BC.
So we have A and C.
Yeah, A
Let's
and C.
use, okay. This will be A squared plus C squared
C squared.
minus B squared. What's the denominator?
To about AC.
Yes, the product of the two adjacent sides. Now we can see how to find the cosine using only the sides.
The same thing as you replace stuff.
Yeah. So in particular, we can see this sides completely determine the angles. We have a formula to find them. Okay, so in this week's homework, we have some applications of law of sines and law of cosine. Okay, I will see you next time. Questions?
Not really.
Okay, okay, okay.